Let's do this with an AVL tree. Let's get things inserting and erasing and keep that nice log-n search performance without incurring n as an insertion cost. We may not be able to get to O of 1 like a linked list or something like that would have for insertion, but we can do it with at least better than n. So, as we saw, the insert may cause the balance factor to become 2 or -2 for some nodes. If we add to the left, then if it was 1, it could become 2, and so on throughout this. So we don't want those balance factors of anything greater than 1 or less than -1. That's tilting too much to one side or the other, essentially. So nodes on the path from the insertion point to the root may have changed in their height or their balance factor, as we saw in the previous example where we inserted the 7 and it changed the balance factor of its parent and the root. It's possible to rebalance the trees using rotation. A tree rotation is just an operation that changes the structure of a binary tree without interfering with the ordering of the elements. That keeps us the order in which things originally were, doesn't do huge alterations to the tree, but it helps us to rebalance our subtrees. For example, that one I was mentioning before, we inserted the 7, it threw off the balance of this binary search tree, but if we look at the lowest unbalanced node, which is on the path from the 7 which was inserted up to the root, so we could look at the 7, see if its parent got unbalanced. It's actually not that bad, so it's fine. But this one the 9 got changed to a balance factor of 2, and that's not an acceptable level. So we look at that lowest unbalanced node, and we shift things around a bit. And once we do that, we get back to perfect balance, and we get back to the best height that we can get for the root here of 2, because we want this well-branched tree and its log n height. We need to do a little more thinking about how we'll do that, though, because there are some examples where a small rotation like that may not give us as clean of a solution as we want, and where there may be some question about which way do we rotate and where do we rotate. We have the lowest unbalanced node here at 19. And we would have to do some rotations around that location. It won't be around the 19 necessarily, but it will be around the location of the 19, where the 10 ends up here. But to do that, we have to find a place for the 20 to live too. And so you'll notice that some things got displaced a little bit, but we'll find that we can do this with only a couple of rotations. So all of the things are still roughly there where they were. The 14 got relocated a bit, and that's about the only major change in the structure, and we're able to get nice balance factors now all throughout here. The tree rotations are applied based on the placement of a new leaf node with respect to the first now unbalanced node. We'll call it alpha, that's found working from that new leaf that you inserted up to the root. You can just check that one pathway from the new leaf up to the root, which will be log n number of steps there. We will deal with the outside cases and the inside cases. Outside will be these left of the left and right of the right. Left subtree of the left child of alpha is an outside one. The right subtree of the right child of alpha is an outside case. Then there are the inside cases. The right child of the left child of alpha, the right subtree of the left child of alpha, and the left subtree of the right child of alpha. And there will be easier or harder cases to deal with based on whether you are outside or inside when you're rebalancing, when you're rotating. For example, if we handle the left outside case, the left subtree of the left child of alpha, then we can do a single right rotation, and that will improve our balance again. So we grab beta, the right child of beta, and we will attach that to alpha's left child, and then we will shift beta up into alpha's place and attach beta to alpha's parent, which is marked as pi here. And that rebalanced our tree. You can see that the blue part here was a little deeper, and now because it's a little deeper, it got shifted up a little bit and now is even with the other ones. It won't always be perfectly even, but it will keep that range of balance factors that we want to have. Some code that would do that is this rotate right function. It is rotating to the right. That is why it has the name rotate right. The node that's passed in here would have been alpha because it's considered the root of our rotation when we're doing this rotation. Beta was the left node. So we take a variable for beta and we set beta's right to be alpha's left. That doesn't lose any data for us there because all it does is disconnect beta from alpha for just a moment, because beta is going to be switched up into the place that alpha was. Alpha was passed in as a reference, so we're able to just switch with alpha there. We don't need to know alpha's parent. We just hold on to that reference to alpha. And we make beta's right be alpha and beta to take alpha's place. And it can be done that simply for this left outside case. It's an O of 1 operation to do the switch there. Inserting will take O of n to find the place to insert the thing, but the rotation for this is O of 1. Handling the right outside case is pretty similar. We just do a single left rotation, which is in many ways the opposite of what we did in the previous situation there. So now we've got this gamma here, which is the right child of alpha, and we're going to need to switch it to be taking alpha's place and to make its left child become alpha's right child. And that's all we do. You'll notice that this doesn't violate any of the binary search tree properties because the left children of gamma will all be greater than alpha. Since gamma was greater than alpha, all of the left children of gamma, because they were to the right of alpha, must, by definition of the binary search tree, be greater than alpha. So we just keep them on the right of alpha, and everything is perfectly fine. And when we switch gamma up, it will have alpha to the left of it, and we know that gamma was greater than alpha, so that's a legal switch as well. So we're careful in the design of this to preserve the binary search tree properties too. The inside cases can get more complicated. If we have the right-left inside case, which we called case C up in our labeled system for this, we need to do a left rotation at the left child, then do a right rotation at the root alpha. This allows us to sort of prepare the nodes to the left of alpha here to be able to do a swap that will actually make them balanced out again, as you can see in the final result. So it's very nicely balanced in this example. Whereas if I just tried to rotate around alpha, all I would end up with is the nodes beneath beta still being stretched too far down, meaning delta here would still be beneath beta and would extend further down than we want it to, also we wouldn't have as easy of a place to put alpha. So we swap around over here, swapping delta for beta and doing that left rotation, and then we swap and do a right rotation. And the right-left case can be handled very simply in terms of code, because if we have a rotate left function, we just call that rotate left function with beta as the root of that. And then we call the rotate right function with alpha as the root in that. So we do that little rotation underneath and then that bigger rotation up above at alpha. I call them little and bigger. The operations will still be O of 1 for both of those. And again, pretty much the opposite is true for the opposite case, the left-right inside case, where it is the left child of the right child of alpha. We sort of phrase these going upwards because to do the checks for where things are imbalanced, we're stepping upwards. So it gives us a similar structure to it. So for the left-right inside case, we do a right rotation at the right child of alpha, and then we do a left rotation at the root, which again, this sort of helps us to arrange things underneath and then to shift them up above, and gives us again a hopefully nicely balanced tree. It will be nicely balanced, again, not perfectly balanced all the time. So to analyze insertion, it costs log n time to find the place you're going to insert in a binary search tree. Search in a good binary search tree is log n. So the best we can do for inserting would be to find the location for it and insert it there. If we have to rebalance, we have to check whether things need rebalanced first. That will be O of log n, because we will have to walk from a leaf to the root, which is, if it's nicely balanced, log n number of steps. And to do any of those rotations is O of 1. Even if we have to do a double rotation, that's 2 O of 1 operations, so it's still O of 1 for the full rotation. Therefore, the largest factor in this is the finding and the walking, which are log n. So the overall insertion is O of log n. Not O of 1 like if we were inserting at the ends of a linked list, but our search will stay O of log n, and our insertion is now lower than the n it might take for a sorted binary array, or binary search ready array that was sorted.